Okay, we'll finish up. Classification of finite groups. Classification of finite groups up to order 15. That's the project in this section. We left off previously having argued that there were exactly two non-abelian groups of order A, the quaternions, and the dihedral group D4. The other sort of problem child case for groups of order up to 15 is 12. And proposition 2.6.4 claims that there are exactly three non-abelian groups of order 12. So let's take a look at the proof of that. Specifically, the claim is there are, up to isomorphism, exactly three distinct non-abelian groups of order 12. Dihedral group, D(6), alternating group, A(4), and a group T generated by two elements, A and B. Element A has order 6. A and B are related like this, and there's another little relationship. So there's the relations. This involves a presentation of this group, capital T. Okay, now the tricky part on this will be to establish that there's only these non-abelian groups. Of course, we've got abelian groups taken care of. That's why there's no comment about this, about abelian groups in this or the previous proposition. We've got abelian groups classified by the fundamental theorem of finitely generated abelian groups. But the chore here is to show that there's only these three possible groups. So we'll put together an argument very much based on the number 12, so it's fairly ad hoc. And these techniques may be partially applicable to other orders, but there's nothing very general about what we're about to do. Also, we're going to relate on the homework exercises for a few of the details. So here we go. First, exercise 2.6.5, speaking of exercises, it's shown that this T actually exists, this group T given by, effectively by this presentation, really does exist and is a group of order 12. And I already know all three of these then are groups of order 12. The big chore is to show these are the only non-abelian groups of order 12. Exercise 2.6.6 is to be shown that these are in fact not isomorphic, D6, A4, and group T. No two of these are isomorphic, so we do get a distinctness of these three groups. Now, to show these are the only possible three groups of non-abelian groups of order 12. So a little bit of general stuff to get us started. It's basically the next couple of sentences. If G is a non-abelian group of order 12, then G has a CeLo 3 subgroup P by the first CeLo theorem. 3 divides 12. 3 is the highest power of 3 that divides 12. So there exists a CeLo P subgroup, CeLo 3 subgroup. In fact, Cauchy's theorem would give us a subgroup of order 3. But let's observe it's a CeLo P subgroup, so maximal, of course. Denote that CeLo 3 subgroup is P, the order of P is 3, and if we look at the index of P and G, Lagrange's theorem tells us we can just take the quotient of the order of G with the order of P. 12 divided by 3 is 4, so we get that index to be 4. By proposition 2.4.8, we know of the existence of a homomorphism, F, between group G and A of S. A of S is the group of all permutations of the set of left cosets of P. Let's take a peek at proposition 2.4.8. Proposition 2.4.8, here we go. Says, let H be a subgroup of a group G. Let G act on set S of all left cosets of H in G by left translation. Somewhat exotic, but we've done lots of that. The claim is, and this is the rest of the part of it, the kernel of the induced homomorphism mapping G into A of S, that is, the group of all permutations on this set S. The kernel of that mapping is contained in H, the subgroup. All right, for us, the subgroup is P. Back to the proof. Homomorphism maps G into A of S. A of S is as described. And the kernel of that mapping, let's call that K, must be contained in P. So this is exactly what we had in the proposition, except the letters are different. By the way, how many cosets are there of P? There's 4, and we counted them a couple of lines back. Since there's 4 cosets, then we're looking at permutations on a set of cardinality 4. So that set of permutations, that group of permutations, is isomorphic to the symmetry group S4 because there's 4 left cosets. All right, so we know the kernel of this homomorphism is contained in P. P is a group of order 3. Kernels of homomorphisms are groups. So we know that K must be either a group of order 3 itself, must be P, or K must be a group of order 1, must be the trivial group, because the kernel is a group and it would be a subgroup of P by the proposition. So that gives us 2 cases. So far, everything's been general. And if you've got any non-abelian group of order 12, then we get to this stage here. We're going to take one of these pieces of information and show that implies G must be one of these non-abelian groups. And we'll take the other piece of information and show that under that condition, G must be one of these other 2 groups. But we get the situation where the kernel of that homomorphism is either P or the trivial group. If the kernel is a trivial group, then we have a homomorphism with a trivial kernel. That's a 1-to-1 homomorphism. Many times we've used this property of the kernel consisting only of the identity, implying that the homomorphism is 1-to-1. For the record, I guess that's theorem 1.2.3. It says that, but we've used that lots of times. In that case, then we've got G under homomorphism F mapped 1-to-1 onto something over here in this group A of S. So the image of G, must be there we go, under F. The image of G must be a subgroup of this A of S to which G is isomorphic. We've got 1-to-oneness by the fact that the kernel is trivial. We got onto-ness because that's what an image means. And it's a homomorphism is how we started this. So we've got a 1-to-1 onto homomorphism. G must be isomorphic to a subgroup of A of S, but A of S is isomorphic to S4. So G must be isomorphic to a subgroup of order 12 of S4. G is order 12, 1-to-1 and onto mapping would produce an image that has 12 things in it. And those 12 things would be isomorphic to, I'm going to pick up the isomorphism right here, isomorphic to a subgroup of order 12 of the symmetry group S4. Symmetry group S4 is of order 4 factorial, 24. So we're dealing with a subgroup of order 12 of this symmetry group of order 24. G must be isomorphic to the group A4. So says theorem 1.6.8. Let's go back and glance at that real quick. 1.6.8 says the part that matters. A sub n is the only subgroup of S sub n of index 2. It's the only subgroup of order half, the order of the symmetry group, n factorial over 2. Okay, that's what we have where n equals 4. So the only subgroup that's half the size of S sub 4 is the group A4. That is the only subgroup of order 12 of the group S sub 4 is the group A sub 4. So G must be isomorphic to A sub 4, and we're already a third of the way there. not in arguments, but in cases at least. So in the event that the kernel of that homomorphism is the identity, G must be isomorphic to A4. The first possible structure of G is established. In this case, we must be dealing with the alternating group A4. But we had two choices here. We had either K equals P or K equals the identity. The kernel of that homomorphism was either P or the identity. In the case that K equals the identity only, A4. We're going to show in the next several slides that if the kernel of that homomorphism is all of group P, then group G must be either the dihedral group or this group T. So that's the plan for the rest of it. So we'll consider the otherwise case, the case in which K equals P itself. In this case, P is a normal subgroup of G. Remember, it was the kernel of a homomorphism. Kernels of homomorphisms are normal subgroups. Theorem 1.5.5 gives us that for the record. So we've got P as a normal subgroup of G under these hypotheses. In this case, P is a unique CeLO 3 subgroup because, remember, any two CeLO P subgroups are conjugates of each other, second CeLO theorem. But when I conjugate a normal subgroup, I just get that subgroup back. It's self-conjugate, if you like, by part of the definition of normal subgroup. Conjugate the group, you get the group back. Theorem 1.5.1, part 5, the laundry list of things that we had that were equivalent, which we took as a definition of normal subgroup. So, since we've got a normal subgroup, then it must be a unique CeLO 3 subgroup of group G. And then G contains only two elements of order 3. If we had, well, we do have these two elements because group P consists of three things: the identity and two other elements of order 3. Group P is, of course, it's isomorphic to Z sub 3, so I can get it somewhat tangible. So there's those two elements of order 3. There can't be any other elements of order 3. If there was another element of order 3, it'd generate another subgroup of order 3. That would be a different CeLO P subgroup, but there's only one CeLO 3 subgroup. So the argument goes, exactly two elements of order 3 in group G. All right, so we're going to look at a couple of elements of group G for a while, put some arguments together, and then shift these elements to two additional elements. So we're going to talk about elements C and D for a while, and then we'll shift over to elements A and B to wrap things up. But we know G contains two elements of order 3. Let C be one of these elements of order 3. Then the index of the centralizer of C and G in group G is the number of conjugates of C. Let's go back and look at that. We've actually used this quite a lot in counting things. But let's go back and look at corollary 2.4.4. So the claim here is the number of conjugates of C is this index involving this centralizer. For the record, again, there's the definition of the centralizer of C. Number of conjugates is this index, corollary 2.4.4. Try to lay all these out and have them ready to go. And it's part 1. The number of elements in the conjugacy class of X, that is the number of conjugates of X, is the index of the centralizer of X in G. In group G. And that's exactly what we have, except we don't, the symbol X, we're using the symbol C. So number of conjugates is this particular index. Some other information, but I think all we need is the link between the index and the number of conjugates. All right. How many conjugates does C have in this case? well, in general, it's equal to this index, but in this case, every conjugate of C has to have order 3. Consider what happens when you conjugate C. I raise it to powers. When I cube it, of course, what we'll get is GC cubed, G inverse. C is order 3, so C cubed is the identity. So we get that the conjugate has order 3 as well. So every conjugate of C has order 3. There's only 2 things in this group that has order 3. There's thing C and that other one. There were 2 elements of order 3. We called one of them C. There's a second one out there as well. We know, however. So the number of conjugates of C and G, this index, must be either 1 or 2. Either C is self-conjugate, conjugate to itself, or C is conjugate to the other element of G. I know conjugates of C have order 3, so there's 2 choices potentially for conjugates. So we get that this index is either 1 or 2. The index can be expressed, Lagrange's theorem, as a quotient of orders of groups, the order of group G divided by the order of the centralizer. The centralizer itself is a group. Lagrange's theorem gives us this quotient thing. Since we have that the index is 1 or 2, and the index is the order of G divided by the centralizer, the order of G is 12. So the only way this quotient can be 1 or 2, when the numerator is 12, is when the denominator, the cardinality of the centralizer, is either 12 or 6, 12 or 6, respectively, to produce an index of 1 or 2, respectively. All right, so we're operating under a situation that is necessary of a group of order 12. We got here by considering the second of 2 possibilities for the kernel of a homomorphism. We're drawn to this situation here. And from here, we'll get to the ultimately to the other 2 groups. In either case, for this is the order of the centralizer, there's a D in the centralizer of order 2 by Cauchy's theorem. If this is a group of order 6 or of order 12, Cauchy's theorem tells you there's an element of order P that divides the order of the group. So there's an element of order 2, no arguments there. There's element of order 4 as well. CELO tells me that kind of thing in the event that the group is of order 12. But no matter how you slice it, Cauchy's theorem still applies to tell you there must be in both cases an element of order 2, regardless of the case. Let's call that element D. And now we're going to have some conversations about this element C of order 3 in this element D of order 2. C is an element of order 3, D is an element of order 2. This plays a big role in the next several computations. All right. We know C is in the centralizer of C, of course. D is in the centralizer and is of order 2. Cauchy's theorem gave us the existence of that thing there. So what's the order of element CD? CD is in the centralizer, it's closed, it's group, closed under the binary operation. So the order of CD divides the order of the group. So what could it be? Well, the group is order 6 or 12. So the order of the element must be divisor, a divisor of 6 or 12. It could be 1, it could be 2, it could be 3, it could be 4, it could be 6. It can't be 12 if this was an element. I'm treating it as a single element. It's written as a product, but treating this as a single element. If this was an element of order 12 and a group of order 12, then we'd have a cyclic group. And I know we ain't dealing with cyclic groups because we're having a conversation about non-abelian groups. So if this if this CD element ultimately in group G was of order 12, then group G would be cyclic. And so it would be a billion. And remember, the whole setting here is G is a non-abelian group. So that's the reason 12 is left out of the argument. Now we'll go through and check these basically one at a time. We'll see that 1, 2, 3, and 4 don't work. It has to have some order. Must be 6. All right. Since D is in the centralizer of C, then DC, D inverse equals C. Right, that's the definition of centralizer up here with G equal to D in this case. So we get that relationship. Multiply on the right by D to get DC equals CD. So we've got a commutativity between these C and D parameters. If CD equals the identity, then the identity is the identity squared. We're saying suppose the identity is CD, so we'll take CD squared. That's CD times CD. It's also CD times DC by that commutativity. That's CD squared C, but D, remember D is an element of order 2, so D squared is the identity, and that produces C squared. So we've got the equation that reads E identity equals C squared. That can't be because C was an element of order 3. Can't have an element of order 3 squaring to give the identity. So we got a contradiction on that. It can't be that C times D equals the identity. Next, consider CD squared. I'm trying to find the order of element CD. CD squared. That's CD times CD. CD times DC, just like we had before, actually. Eliminate the parentheses, you get a D squared, becomes an identity because D is of order 2. And we've got C squared. C squared can't be the identity since the order of C is 3, just as before. So we can't have CD equals the identity. We can't have CD squared equals the identity. Let's consider CD cubed. Right, so we're very much just going through case by case and beating this to death until we can find the order of that element. CD cubed, CD, CD, CD. Let's write that as CD, DC, CD. Then we get let's see, there's a D squared and a C squared. It simplifies to C, D squared, C squared, D. Oh, but wait, D squared, that's the identity. D was an element of order 2, previous slide. Replace that with the identity, produces C cubed D. Oh, but C was an element of order 3, so that's the identity there. This gives us simply D, and D's not the identity. D's an element of order 2. Neither C nor D are the identities. So we've drawn the conclusion that CD cubed is also not the identity. Let's try CD to the 4th. CD to the 4th, how about we write it as CD cubed times CD? And we just saw that CD cubed reduced down to D. So we can write CD cubed times CD as D times CD. Got the commutativity. Take the CD and write it as DC. Those two commuted. Gives us a D squared C. D is order 2. So it's gone. We get C itself. And C is not the identity. We're checking the possible orders of element CD. Those possible orders were 1, 2, 3, 4, and 6, because they had to divide 12 and couldn't be 12. 1 didn't work on the previous slide. 2, 3, and 4 haven't worked. The only choice is 6. Just make sure. Let's take CD to the 6th power. That'd be CD cubed, CD cubed. We saw CD cubed equals D a couple lines back. So this is D times D, D squared. Yeah, D is an element of order 2, giving us the identity. And the order of this element CD must be 6. All right. We're going to shift gears again and take this from a conversation about these elements C and D and introduce some elements A and B. First, let element A equal this element CD produced above. You know A has order 6. The order of CD is 6, so element A has order 6. All right, we did something like this actually in the previous proposition. So A is an element of order 6. That means A generates a subgroup of G of order 6. G is of order 12. So, hey, this is a normal subgroup. Has index 2. It's half the size of the group. When we deal with finite groups, I can talk like that. So a subgroup of half the size of group G, when G is a finite group, is a normal subgroup. It's proposition 2.6.3 was the last thing we did. It's a normal subgroup. We've dealt with this a number of times. When a subgroup is half the size of the big group in finite groups, you got yourself a normal subgroup. When the index is 2, you've got a normal subgroup more generally. But that gives us a normal subgroup of group G. Its index is 2, or if you like, I can look at the quotient group there. What we'll get then is group G can be written, let's look down here in this second bulleted comment. Group G then is the coset subgroup generated by A, and then a left coset of that. There's 2 cosets of this group in G, this thing itself, and another one. For the other one, there must be some B in the group. B is not in that first coset. B is not the identity. And B squared is in this group. And for this last little part here, no surprises with these 2 things. This last little part, look through the proof of proposition 2.6.3. We did the same kind of thing there and found a B not in one coset, such that the square of it had to be in the other coset, and put together an argument as to why B squared was in this particular identity coset. So group generated by A is normal. So if we take BAB conjugate, then that'll have to give you an element of that normal subgroup, definition of normal, one of the pieces of definition of normal. So BAB inverse is in this group generated by A. That means BAB inverse is some power of A. Which power is it? And similar to what we did upstairs with the powers of CD, we're going to look at BAB inverse equals powers of A and see what possibly that could be. So we consider the value of BAB inverse in terms of an expression of it as a power of A. We'll get a bunch of contradictions, leaving us with 2 choices. And those 2 choices will lead to the 2 possible other structures for group G. What if BAB inverse equals the identity? Then BA equals B, multiply on the right by B. That only occurs when A equals the identity. A is not the identity. A is an element of order 6. So it's not the identity. How about BAB inverse equals A to the first power? Cross multiply, BA equals AB. Here's what we're dealing with, and this was similar to something we had in the previous proposition as well. We get then G generated by A and B, because if we've got commutativity, we'll have this coset, we'll have the other coset, then every element of G can be written as a power of B times a power of A. Again, details given in that previous proposition. But if we get the A's and B's commuting, then we get everything in group G commuting. So G would be an abelian group. It's not an abelian group. This is a conversation about non-abelian groups. Let's try to set it equal to A squared. What if BAB to the B inverse, BAB inverse equals A squared? Then cube both sides. That gives us an A to the 6th on the right. A to the 6 is the identity because A is an element of order 6. It came from here. BAB inverse cubed would be BA cubed B inverse. Equals the identity. What's that imply? Multiply both sides on the left by B. That implies BA cubed equals B. Well, that can only occur if a cubed is the identity. It's not. It's an element of order 3. A cubed doesn't equal the identity. Let's set BA B inverse equal to A cubed. I promised you some tedium. Let's square both sides. We're going for getting powers of A involving exponents of 6, a to the 6th, because we know that's the identity. So that's why cubing the square and squaring the cube to get the a to the 6th. Square both sides. Multiply this out, we'll get b a squared, b inverse, there you go. A cubed squared is a to the 6th. A to the 6th is the identity because a is an element of order 6. What can we do with that? See, ba squared, b inverse equals the identity. Multiply both sides on the right by b. Ba squared equals b. Can't have that. That would imply a squared is the identity. A squared can't be the identity because it's an element of order 6. All right, so a to the 0 didn't work. A to the 1 didn't work. A to the 2 didn't work. A to the 3 didn't work. It's got to be some power of a because we know ba b inverse must be in the group generated by element A. It comes from the normality of that group. What's left? 4 and 5. Let's try 4. What if BA B inverse equals a to the 4th? Then BA B inverse cubed equals a to the 4th cubed, producing an a to the 12th. Well, that's the identity. So that's why we raised it to the 4th power, raised it to the 3rd power to get the identity out of the power of a. On this side, we get BA cubed B inverse. There you go. That equals the identity. Multiply on the right by b, BA cubed B. That implies a cubed equals the identity. That can't be because the order of a is 6. So BA B inverse must be some power of a, and it ain't the 0th, 1st, 2nd, 3rd, or 4th power. It must be the 5th power. Remember, A generated a subgroup of order 6. So we must have a to the 5th, or if you like, A inverse. It's an element of order 6. So a to the 5th and A inverse are the same. It must be that BA B inverse equals A inverse. I can take that and multiply both sides on the right by B to get BA equals A inverse B. We can take the A to the other side on the right to get ABA equals B. And we're going to play with ABA equals B. But let's take a little pause. BA equals A inverse B. And this is necessary. What was the statement of the theorem? Back to the original statement. It involved this BA equals A inverse B, at least for group T. And I think that was related to the dihedral group as well. So that's good news, I guess. So I see this thing pop up. By the way, we've seen that the order of element A is 6 as well. So we're getting close. All right. So we have established this. It's equivalent to ABA equals B, and it's this thing we're going to manipulate now. Remember, we got here by saying B is not in the group generated by A, but B squared is. So let's see what B squared is in terms of powers of A. So similar to what we had before, we've got an element of this group here. Then I know this thing, this B squared, must equal some power of A, because that's the only thing here. A to the 0, A to the 1, A to the 2, A to the 3, A to the 4, A to the 5. So let's check those and see what happens. So that's what, 6 things to check. Well, what we're going to do is show 4 of them don't work. So the other 2 are possible, and that's where the other 2 groups will come from. Okay, let's try. So we've gone through them in kind of an oddball order, but let's try B squared equals A squared. That power of A. We're working under the assumption here. We've derived the fact that ABA equals B. So that we'll use, like I said, repeatedly. ABA equals B. We can square both sides of that to get ABA squared equals B squared. ABA times ABA equals B squared. That would be A squared. The two A's get together. Times BA equals B squared. A squared, you can replace A squared with B squared under these conditions, under these hypotheses. A squared and B squared are the same, so replace that A squared with a B squared. All right. That's given us equals B squared. Let's see, where's this B squared coming from? Oh, the right-hand side of the equation. Okay. So copy this over, replace the A squared with a B squared. Okay. Giving us AB to the fourth, right? B squared B, right? AB to the fourth A equals B squared. B squared and A squared are the same in this case, we've supposed. So we can change the B squared to an A squared on the right-hand side of the equation. We can cancel these two A's with these two A's to get B to the fourth equals the identity. If B to the fourth equals the identity, then under the assumption that B squared equals A squared, B to the fourth equals A to the fourth, square both sides, we get A to the fourth equals the identity. A contradiction, element A has order 6. So B squared is some power of A, that power ain't 2. Let's try 4. If B squared equals A to the fourth, well, A has order 6, so A to the fourth and A to the negative 2, same thing. We know ABA equals B. We've derived that. We can rewrite that as B equals A inverse B, A inverse. Take the A's to the other side of the equation. Square both sides of this. B squared equals ABA inverse times itself. That would be A inverse B, A to the negative 2 times B, A inverse. A to the negative 2 is the same as B squared. So we, in this case, in this hypothesis, we hypothesized that. So we can replace the A to the negative 2 with a B squared. That'll give us A inverse B, B squared B. A inverse gives us a B to the fourth, sandwiched between a couple of A inverses. B squared equals A to the fourth, our hypothesis again. So we can take this B squared, replace it with an A to the fourth on the left-hand side of that equation, keep the right-hand side the same. Take these A's to the other side of the equation, and A to the sixth equals B to the fourth. A is an element of order 6, so we get the identity equals B to the fourth. B to the fourth is the same as A to the 8th. Square both sides here. Replace the B to the fourth with an A to the 8th, and we get the identity equals A to the 8th. But the order of A is 6, so A to the 8th is the same as A squared, and A squared doesn't equal the identity. A is an element of order 6. Okay, so B squared is some power of A, and that power ain't 2 or 4. Let's try 1. Like I said, we've gone through them in a kind of oddball way. These last two arguments are a little bit different. Suppose B squared equals A to the 1 power. Then raise both sides to the 6th power. We get B to the 12 equals A to the 6. That's the identity because A is an element of order 6. Then we know, so we're checking for the order of B here. So what we're doing, trying to show B as a generator. Yeah, we're checking the order of B. So B to the 12 equals the identity. The next little observations are going to allow us to conclude that B is an element of order 12. I mean, it's got an order that divides 12 by this little relationship, B to the 12 equals the identity. Let's show it's not something smaller than 12. What about B to the 6? Well, we can cube both sides here. We know B to the 6 equals A cubed. That's not the identity because A is an element of order 6. How about B to the 4th? We'll square both sides. B to the fourth is a squared. That's not the identity because a is an element of order 6. B cubed. How about this? We multiply both sides of this equation, say on the right, by b. Give us b cubed equals ab. AB can't be the identity, or else B would be the inverse of A. If B were the inverse of A, then B would be in the group generated by A, and it's not. And that's where we got B from. It was something in group G that wasn't in the group generated by element A. So that can't be the case. So we know B to the 12th is the identity, B to the 6th is not the identity, B to the 4th is not the identity, B cubed is not the identity. B squared is not the identity because B squared equals A, and A is not the identity. So the order of element B must be 12. But then we've got an element of order 12 in this group G. That means G is generated by that element B. But G can't be generated by a single element. That means G is cyclic. That means G is abelian, and we're not dealing with an abelian group. So this argument, different from the ones above contradicted orders of elements. I guess in a sense this one did as well. But under this assumption, we were able to show that G is generated by the single element B, and that can't be. That would give an abelian group. How about B squared equals A to the 5th? That's a power we haven't tried yet. Then raise both sides to the 6th power. Get B to the 12th equals A to the 30th. Well, that's the identity because A has order 6. So B to the 12th equals the identity again. Let's look at B to the 6th, B to the 4th, B cubed, B squared is sitting right there, and draw the conclusion again that B has order 12. B to the 6th, let's see, cube both sides would give us A to the 15. A is of order 6. So mod the exponent out, mod 6. That leaves A cubed. A cubed is not the identity. B to the 6 is not the identity. B to the 4th. Square both sides. A to the 10th. Mod 6 it. A to the 4th. A to the 4th is not the identity. A is an element of order 6. B cubed. Multiply both sides on the right by B, as we did above. To get B cubed is A to the 5th B. That's not the identity. If it were, then B would equal A. I'd need A to the 5th inverse to get the identity out, and B can't be A itself. Right? We chose it to be something distinct from A, something distinct, in fact, from the elements generated by A. So B to the 6th is not the identity. B to the 4th is not the identity. B cubed is not the identity. B squared is A to the 5th. That's not the identity. And B to the 12th is the identity. So B is an element of order 12. You can't have that again. It's the same contradiction as we had above. That would mean G is generated by element B. That would mean it's a cyclic group. It's an abelian group, and we're not dealing with abelian groups. So how are we doing here? B squared is not A to the what? Let's look at the previous slide real quick. It's not A squared. It's not A to the 4th. It's not A to the 1. It's not A to the 5th. So that only leaves two possibilities. B squared was the identity, A to the 0, or B squared is A cubed. We hadn't done those two. So there's the two possibilities on the value of B. We've got G generated by elements A and B. Element A has order 6. Agreed, both cases. We had BA equals A inverse B, both cases. The difference was whether this element B was of order 2 or this element, well, I guess I could explain it as this element B squared is A to the 0, the identity, or was A cubed. So there's the two possibilities we had. So Very first case, the kernel was trivial in that homomorphism. We were dealing with the alternating group A4. Second case, kernel of that homomorphism is not the trivial group. It was that group of order 3. Led to two possibilities, this and this. In the event that we have an element of order 6, b squared equals the identity, we have this relationship between A and B are generators of a group, then we have the dihedral group D sub 6. Theorem 1.6.3 gave basically a group presentation. Now, they didn't use that terminology at the time. Group presentation of dihedral groups in terms of two generators. Here, we've got b squared equals a cubed. This is that second group. These were the conditions on that second group. Exercise 2.6.5 dealt with showing that you get up to isomorphism, that group T, that group T mentioned before. That's all the possibilities. So here's the other two possible structures of group G. And that's how you show there's only 3 non-abelian groups of order 12. Okay, let's use all this stuff now. So the messiness was the groups of order 8 and restricting it to show there's only 2 non-abelian groups of order A. And this thing, there's only 3 non-abelian groups of order 12. About this second group, the one we denoted T, group T of order 12 is an example of a dicyclic group. A presentation of the nth dicyclic group, denoted, let me read this as dice sub n. It's given by sets X and Y, where X contains the 2 generators. Y implies 3 relations. The relations implied by Y are A to the 2n equals the identity, A to the n equals b squared, and B inverse AB equals A inverse. This is effectively what we had before. When we plug in n equals 3, we had A to the 6 was the identity, we had A cubed equals b squared, and we had this. When n equals 3, dicyclic group dice sub n, that's that group capital T we were talking about. So here's a category to put that group in. The group dice sub n is of order 4n, so when n is 3, it'd be order 12. That checks out. Here's your reference on more details on that. Rotman's book on fundamentals of group theory and advanced approach, and even some pages referencing these dicyclic groups. So the group T actually is the third dicyclic group. When n equals 1, the first dicyclic group be a group of order 4. Claim is it's isomorphic to the integers mod 4, so it's abelian. When n is greater than or equal to 2, the dicyclic groups are non-abelian. In fact, when n equals 2, we get the quaternions. So these dicyclic groups encompass the exotic groups that we've encountered up through order 15. The exotic groups are the quaternions in this group capital T, and they're both examples of dicyclic groups. When n is a power of 2, the dicyclic group dice sub n is isomorphic to what's called a generalized quaternion group. So there's yet another category of finite groups out there. All right, we want to classify groups up to order 15 and get some general stuff, hopefully. There is no formula, quoting Hungerford from page 98, there is no known formula giving the number of distinct, that is non-isomorphic groups of order n for every n. There's some partial progress. We're going to deal with groups up to order 15 because we got the equipment to do that. Those last two propositions, very clunky equipment. Without that, though, we'd gotten stuck on how many groups there are of order 8 or 12. For prime orders, exercise 1.4.3 tells us there's only one group of a given prime order. And in fact, it's a cyclic group. So it's an abelian group. So with an eye towards 1 through 15, for the prime orders, 2, 3, 5, 7, 11, and 13, only one group of those orders. Groups isomorphic to Z sub P, where P is those particular prime values. Corollary 2.6.2, that dealt with twice a prime 2P. If I have a group of order 2P, where P is an odd prime, so this covers 6, 10, and 14 in the range we're interested in. There were two non-isomorphic groups of order n. They were the integers mod n and the dihedral group d sub n over 2. We dealt with this as 2p, and we had the integers mod 2p, and we had the dihedral group d sub p, was the way it was stated in the corollary. So that takes care of 6, 10, and 14. Exercise 1.4.5 tells you there's two groups of order 4, only the integers mod 4 and then the direct sum of the integers with the integers. Actually, I might want to view 4 as the square of a prime. More of that very soon. But we can establish this from one of the exercises, say. Theorem 2.2.1, let us classify abelian groups, finite abelian groups. Proposition 2.6.3 dealt with groups of order 8. We got a total of 8 groups of order 8. We've got the abelian ones, that's theorem 2.2.1, gives the abelian ones various powers of 2 and direct sums. The non-abelian ones we know by proposition 3 from this section, quaternions and dihedral group d sub 4. Exercise 2.5.13, and a little bit more of that in a sec, allows us to classify groups of order 9. Turns out they're abelian. A group of order p squared is abelian. So that's what this result says. We know how to deal with abelian groups. P squared, we'd have 3 squared. We'd have z sub 9 and z3 direct sum z3. Hey, look at that. That's the same type of behavior we had when p equals 2. We were looking at 2 squared, and that pattern holds for general p squared. We'll state this in a little more depth here shortly. 12. Theorem 2.2.1 and proposition 2.6.4 classify the 5 groups of order 12. The abelian ones, 2.2 was abelian groups. So the abelian groups of order 12 are simply Z12 and Z6, direct sum Z2. And the non-abelian groups, after that rather lengthy stroll through the proof of proposition 6.4, it's the alternating group A4, the dihedral group D6, or this, what we saw was ultimately a dicyclic group, this group of order 12 denoted with a T, say. That just leaves 15. Hey, 15 is a product of 2 primes. The very first proposition we did in this section said, suppose we have a group of order PQ, where P is greater than Q. It was something about Q divides P minus 1 or not. So there were a couple of different cases there. Proposition 2.6.1 classifies the groups of order 3 times 5 simply as the group Z sub 15, product of 2 primes. We got a product of 2 primes, P and Q, 2 distinct primes. We got it covered by that proposition. So if we look at 1 through 15, here's the justifications in a little table. I gave the justifications before the statements just to make it fit on a page, really. But up through order 15, there you go, in terms of justifying the following larger table that lists all groups of order up to 15. Let's take a quick look at it. Of course, there's only one group of order 1. The primes, we get one group. For 3, the alternating group A3 is isomorphic to the cyclic group Z3, but it's only one group of order 3. First order, we get 2 distinct groups as 4. The integers, or the integers mod 4 versus the Klein 4 group. 5 is prime. 6 is 2 times a prime. We get 2 of those. Run across the smallest non-abelian group, the dihedral group. Your first exposure to groups, symmetries of a triangle And, you know, just popular level explanations of what group theory is, they go to symmetries of the triangle. So dihedral group is interesting because it's not commutative and it's geometric symmetry of a triangle. Also isomorphic to S3, by the way. 7 is prime. 8 we went through in some detail. 9 is a prime squared. More of that shortly. 10 is 2 times a prime. Yeah, product of 2 primes. You know, 15 is a product of 2 primes as well. This is behaving differently. Yeah, it's because 2 divides 5 minus 1. We get 2 of them in that case. So we get a cyclic one and a dihedral group in that case. 11 is prime. 12, we went through in great depth the story about groups of order 12. Easy to find the abelian ones and mildly nightmarish to show there's only 3 non-abelian ones, but there they are. 13's prime. 14's twice a prime. And 2 divides 7 minus 1. So we get 2 of these. It's twice a prime. 15 is a product of 2 primes, but 3 doesn't divide 5 minus 1. And in this case, we only get 1, applying that proposition 1 from this section. And there's groups 1 through 15, orders 1 through 15, classified. What if we looked at 16? I only mention because there's a little AMS paper out there that addresses this. There's 14 groups of order 16. 5 of them are abelian. Well, those 5 are easy to find. It's a Z16, direct sum of Z2 and Z8 and so forth. So it's easy to deal with the abelian ones. Showing there's only 9 non-abelian groups. I'm not sure how they deal with this in this paper. An AMS paper, this is accessible through the eTissue library if you have your login credentials. And the title of this paper from 2005 is The Groups of Order 16 Made Easy. The easy part, and I'm quoting from the abstract here, I'm gonna hack through this little paper, says doesn't use CELO theorems, doesn't use P groups, generators, relations, doesn't use group action. Well, that'd be easier, I guess, in some of this stuff we've been through. How they tie down that there's only that many groups, I'm not so sure. Many of these groups, about half of them involve products. So we've got the regular old direct product of groups or direct sums of groups that we've dealt with. And this semi-direct product ideas come up in passing, and it's mentioned in some of the exercises. So several of these involve products of some sort of a group of order 2 with a group of order 8, be it a direct product or a semi-direct product. If we want to go beyond order 16, then some of them are easy. Groups of order prime are easy. Want to go beyond 16? Hey, 17, piece of cake. It's prime, one group, Z sub 17. 19, piece of cake, one group, Z sub 19, because they're prime. 21, product of 2 primes, 3 and 7, tells us we get 2 groups, Z sub 21, and another group, a non-abelian group of order 21. As explained in proposition 2.6.1. I call it kind of a mystery group based on the fact that it's order 21. What could it be? Well, it ain't a symmetry group. Symmetry groups are order n factorial, and there ain't no factorial that equals 21. Alternating groups are n factorial over 2, so it ain't an alternating group. Dihedral groups are of order 2n, 21's odd. Dicyclic groups were 4n. It's not 0 mod 4. So it's none of those. Even with a new category, the dicyclic groups introduced. Whatever group this is, it doesn't fall in any of those categories. Order 22, that's 2 times the prime. So we know what happens there. Exactly, it's the integers mod 22 and the dihedral group D sub 11. 2 times 13, 26. We get the similar kind of behavior. If you're into this kind of thing, there's a link in the notes to a document called Tribomaximal Mixing from Small Groups that gives a listing of all groups of order up to 100. There's also something called a GAP, Small Groups Library. GAP stands for Groups, Algorithms, and Programming. So there's a link to that. Enjoy yourself in terms of dealing more with finite groups. But for something general, like parting observations from this section, hey, if P is a prime, there's a single group of order P. It's up to isomorphism, it's Z sub P. Exercise 1.4.3, we mentioned it several times, tells you such a group is a billion, and once you know that, then you can deal with the fundamental theorem of finite abelian groups and say it's got to be Z sub P. Actually, if it's order P, it's got to be cyclic, so maybe there's a quicker way. How about P squared? Suggested this in our previous conversation, but it wasn't stated clearly. There's only two groups of order P squared where P is a prime. Z sub P squared and the direct sum of Z sub P with itself. Exercise 5.13 will tell you that a group of order P squared must be a billion. That's what I was thinking of. If it's a billion, now I can appeal to the fundamental theorem of finitely generated abelian groups to get these as the possible structures. So order P squared, taken care of. How about order P cubed? Hungerford doesn't go there, but let's play with P cubed a little bit. I can tell you what the abelian groups are. That's no breaking news there. Even when P equals 2 and we looked at 2 cubed, we had the abelian groups, and then we had these two non-abelian groups, the quaternions and the dihedral groups. For P an odd prime, so P not 2, there's two non-abelian groups of order P cubed. I guess actually Hungerford does deal with that part of it. Exercise 2.6.8. One of these groups has generators A and B, where A has order P squared, B has order P. Here's a relation between those generators. The other has 3 generators, all 3 of them generators of order P, and there's some relationships between those. I've linked to a, it's not very long, document on groups of order P cubed by Keith Conrad of the University of Kentucky, I'm sorry, University of Connecticut. That goes into this groups of order P cubed in a bit more depth. One example of a group of order P cubed is these Heisenberg groups based on Z sub P. So the elements of the group are these 3x3 matrices, and we're choosing A, B, and C, not to be confused with the generators mentioned up here. These are numbers from Z sub P, the field Z sub P. So there's P choices for A, P choices for B, and P choices for C. So there's your P cubed. Trusting that, in fact, these matrices under usual matrix multiplication do, in fact, form a group. Closure I would worry about, but they're closed. And you've got inverses as well, because you're dealing with upper triangular matrices, and you're taking these entries from a field. There's a class about group theory, so we don't get into the field stuff too much. But the integers mod P form a field, giving you multiplicative inverses within that algebraic structure. You could choose the A's, B's, and C's to be from any field, in fact, and you'd get a group. Here's some of the finite fields. There's other finite fields to choose from. We could use the real numbers. If we chose A, B, and C to be from the field of the real numbers or the complex numbers, we get something called a continuous Heisenberg group, which apparently pops up in applications in one-dimensional quantum mechanical systems. Yeah, anyhow, that's why the physicist Werner Heisenberg, Heisenberg's uncertainty principle guy, that's why his name's associated with this particular group. I have a little supplement, really, that I use in the senior level algebra class on small groups, which overlaps a lot with what we did in this section, not so much the gory stuff with dealing with groups of order 8 and 12. but gives a list of groups of small order and talks in general about some finite groups and mentions this fairly famous document, the Atlas of Finite Groups, and deals with a monster group, where it comes from and what its order is. The monster group is a gigantic group. Well, a monstrous group, but still it's just a finite group, but it's of order 10 to the 50 some odd, if memory serves. And that will do for our classification of finite groups. Well, we made it up to order 15 in some special cases like primes, p squared and p cubed as well, if you'll accept those p cubed results. So have a nice day. We'll move on to something somewhat different in the next section, and I'll see you there. Bye-bye.